Hi, everybody. Here we are, ready to start chapter one of our number theory text. And here I am at lovely Hogwarts. I should get a little congratulations. I did get accepted. It's an honor being here at Hogwarts. And I don't want to make you too jealous, so I'm not going to talk about it that much. We're going to go right to some math. And here we go. Let me share my screen with you. And whoops, that's not what we want. We want that right there. Okay. So this is, let me just move this here. This is the chapter one of the, actually, you know what? Let me scroll back a little bit. This is our textbook, The Theory of Numbers, by Robert Carmichael. It's a fabulous textbook. And this is what we're going to be starting with. We're going to be using this textbook for the first part of the course, and then later we're going to switch to the second textbook, Applied Discrete Structures. That's going to come later. And both of them are fabulous, and as you know, both of them are free. They're free PDF downloads, so we're all good. Okay, everybody. Excuse me. Let's rock and roll here. So here we go to chapter one: elementary properties of integers. Okay, now first of all, we're going to be studying when in the study of number theory, we generally are restricting ourselves to studying positive integers. And a lot of times we'll say a word like integer or we'll say a word like number, but we really mean positive integer. Let's just get that off the bat. And furthermore, we're not going to go through any fancy schmancy definitions of what the positive integers are, or sometimes we call them the natural numbers. We're not going to go into any fancy additions. We're gonna suppose that the integers is already defined, either by the process of counting or otherwise. There are fancier ways of doing that. For example, something called Peano's axioms, which is this right here. And Peano's axioms are, this is a good thing to know just because it's very famous and very basic. Zero is a number. If A is a number, the successor of A is a number. Zero is not the successor of a number. You see how these things are all true. Two numbers of which the successors are equal are themselves equal. That makes sense. And induction axiom, this is a big one. If the set S of numbers contains zero and also the successor of every number in S, then every number is in S. Meaning if I have a set of natural numbers and that set contains the number zero, by natural number, I mean positive integer. If I have a set of positive integers and that set contains the zero, and every time, for every element that's in the set, the next integer is also in the set, well, if it has zero, that means it has to have one, because one is next. If it has one, then it has to have two, because two is next, and so on and so forth. You wind up having the entire set of positive integers, and that's actually called induction. We do a lot. We prove a lot of things. We use induction a lot to prove stuff, and that is the famous Peano axioms. Anyway, back to our text. Back to us. So it immediately follows the sum of any two integers is an integer. The difference of any two integers is an integer. These are things which you just kind of know from experience. And the product of any two integers is an integer. And these are things which I think you'll all agree. We don't need a whole big giant proof of this. Most of the stuff you just kind of know. Some other very fundamental theorems that we're just going to say without proof. Again, this is stuff we kind of know, is A plus B equals B plus A. That's commutative law for addition. A times B equals B times A. Again, commutative law for addition. A plus B plus C equals A plus parentheses B plus C. So if I shift the parentheses and I'm doing addition, it all comes out the same. This would not work with things like subtraction or something, but for addition it works. And it works for multiplication. A times B times C equals A times B times C. It doesn't matter where the parentheses is, it comes out to the same answer. And eighth, which is very important, I think, is distributive property. A times B plus C is equal to A times B plus A times C. And that's the distributive. These are things you've seen many, many, many times. We're just saying that these things are true for the natural numbers, for the positive integers. And let's take a look at some induction. So here's an example. Let's just take a quick look here. Let's take a look at that first problem. 1 plus 2 plus 3 plus ... plus n is equal to n times n plus 1 over 2. Let's take a look at that. So I'm going to actually drew up a hand. I have a little picture here. So the step one, I want to show that it works for n equals 1. There is no n equals 0 here, so I'm going to show n equals 1, the smallest number. So 1 is equal to 1 times 1 plus 1 over 2. That's the formula. And of course, that's equal to 1. So we see the formula works for n equals 1. Step 2, I want to show is that if it ever works for a value of n, I want to show that it's always going to work for the next value, n plus 1. And that's going to be the induction argument in the piano axioms, meaning because if it's true for 1, that means it's got to be true for 2. If it's true for 2, it's got to be true for 3. True for 3, there has to be 4. It becomes like a domino effect. So let's say we have an n where this works. We do know we have an n. We know it works at n equals 1. But let's just look at a random n. So 1 plus 2 plus 3 ... plus n is equal to n times n plus 1 over 2. That's what we're looking at. And now let's go to the next case. So I'm taking this side right here, 1 through n, and I'm adding on the next number, the n plus first number. So I'm going to add that number on to both sides here. Well, n plus 1, I want to get a common denominator here, so multiply this by 2 over 2. And I have n times n plus 1 plus 2 times n plus 1. Notice there's a common factor of n plus 1. I combine these guys, and I get n plus 1 times n plus 2 over 2, which is the same thing as n plus 1 times n plus 1 plus 1 over 2. So we see that when it's true for n, which that's what we're given here, it's true for n, which is true for some n, then I've shown that being true for n will automatically make it true for n plus 1. And I know it's true for n equals 1. That means 1 automatically makes it true for 2. 2 automatically makes it true for 3. Then automatically 4, 5, 6, 7, forever. And that is what we call a proof by induction. I want to show you this. Let's just take a look at this. Let's test it out a little bit. So we're just going to make a little spreadsheet, open up a little spreadsheet here. And we have here, let's see, how are we going to do this? I don't know. So I have a bunch of numbers here. And now here I want to find, this is going to be equal to, listen, I think the easiest way, I'm just going to make this equal to 1. And this I'm going to make equal to, I think it's the easiest way to do this. Maybe better ways and easier ways. This is the way of 2 plus whatever that's up there. And now if I extend this, let's see. Also one more. Oh, I see what I did. Let's try that. Okay, so 1 is 1. 1 plus 2 is 3. 1 plus 2 plus 3 is 6. 1 plus 2 plus 3 plus 4 is 10. That's bowling pins, in case you're wondering. 1 plus 2 plus 1 through 1 plus 2 plus 3 plus 4 plus 5 equals 15. 1 plus 2 plus 6 equals 1. So you have all these numbers here. Now, what I want to do over here is I want to look at this column going to equal to this number right there times that number plus 1. And divided by 2. And why did that not work? A A1 times A1 plus, oh, I meant to do divided by 2. I looked at the divided by 2. Okay, and now let's check these out. We got the exact same numbers. So this column here, column D, is n times n plus 1 divided by 2. And column B is adding up the sum of the n numbers. So we see that these two columns, 21, 21, 66, 66, we see that they wind up being exactly the same number. By the way, these numbers here are referred to, these numbers here are referred to as triangular numbers. I'll let you figure out the geometry of why that is, but they're called triangular numbers. Well, well, I think that's going to conclude our very first, that's going to conclude our first little tape, a little lecture. So we're going to end the tape right now, and we'll resume next time. Bye.